This video provides an academic overview of the Bayesian model for stroke diagnosis project, highlighting its objectives, methodology, and key insights. Stroke is the second leading cause of death globally with a high societal impact, yet early diagnosis remains a critical challenge in healthcare systems and environments. My project aims to tackle this problem by building a Bayesian model that empowers doctors to predict stroke risk using causal relationships and probabilistic reasoning. But why Bayesian networks? Well, doctors want answers and to understand risk, not just numbers. The key issue here is traditional AI models like neural networks can't explain definitively why a patient is at risk. Doctors need interpretable tools to act on predictions. So this motivated me to focus on building a simple Bayesian model that shows how specific risk factors interact to predict stroke risk. So how did I go about this project? Well, I first familiarized myself with the software, Agena, and worked towards building a simple introductory Asia model. With that built and the ongoing learnings through the Bayesian module, I transferred these key skills into making my Bayesian model for stroke diagnosis. I initially conducted data pre-processing, where I cleaned a Kaggle dataset, my main data source, to make predictions, handling missing values through data cleaning using Python and Panda libraries. Age and glucose levels, initially continuous variables, were dynamically discretized to make the Bayesian model more interpretable and easier to understand and model. The design and development behind building the Bayesian network involved taking an incremental and iterative approach, assessing how certain risk factors influence the prediction node, and using sensitivity analysis to evaluate and identify if specific risk factors are more influential than others in determining stroke risk. I started off by saying how just three risk factors, age, gender, and smoking, influence stroke risk, then expanded to 10 nodes, continuously refining node probability tables. I began exploring how individual risk factors at first have a direct causal link to stroke risk. I later amended this by using indirect causal links to incorporate better causal meaning and to align better with medical knowledge. By structuring causality more naturally, the model can provide better insights into risk factors instead of just correlations. Sensitivity analysis further revealed heart disease and hypertension as the strongest predictors, supported by literature findings. Let's consider a use case scenario and explore how the Bayesian network predicts stroke risk. Let's dive in. The following model learns from data and incorporates expert judgment. Each node graphically represents a risk factor in the Bayesian network, showing the initial prior probabilities in each state of a node. The target or predictor node in this Bayesian network is the has stroke node. So let's consider a male patient. In the model, this causes a slight reduction in stroke risk, reflecting the dataset's pattern, even though medical literature generally suggests males have a higher risk, showing the influence of the training data and potential biases. Next, I set the patient's age to the 50 to 70 range. The stroke risk increases, which is expected. This change dynamically updates related nodes, specifically BMI, hypertension, and average glucose levels, through forward causal links. Here, age indirectly impacts stroke risk by nudging these intermediate factors. I now input that the patient's BMI is obese. This further increases stroke risk by updating both the hypertension and average glucose nodes. This also contributes to forward causal links. The model, in addition, does back inference. Even though marital status is still unknown, the fact that the patient is obese suggests there is a good chance he might be married, so that node's probability is adjusted accordingly. I now specify that the patient has heart disease. So this directly boosts stroke risk and also initiates back inference on other nodes. Because heart disease is now observed, the network adjusts our belief about his work type and smoking status, indicating these unknown factors could be linked to his heart condition. I find out further that the patient is a smoker. And you see that stroke risk does not change any further. Well, this is due to an explaining away effect, since heart disease, an already strong predictor of stroke, is confirmed, so the additional information from smoking becomes redundant and its impact is blocked. The final stroke risk is dynamically updated through forward inference and moderated by back inference, conditional independence, and explaining away. This allows doctors to better understand the chance that a patient might be diagnosed with a stroke, see exactly why a patient is at risk, and how much a risk factor contributes in the probability of stroke risk despite incomplete information, and make informed data-driven decisions. In the medical context, even a small increase in absolute stroke risk can be hugely significant. This is because baseline risk plays a major role in clinical decision making. Doctors often act based on relative changes in risk and how interventions might shift that probability. Bayesian networks uniquely enable this kind of reasoning, highlighting not just whether someone is at risk, but why and how much, based on observed evidence. So, just to conclude, although this model is simple and has to be carefully considered before implementing it in healthcare systems, its base and foundation serve as a decision support tool that bridges the gap between data and clinical action. Due to the sustainable nature of the model, its impact on society and future vision could be adverse if integrated with electronic health records for real-time updates and if expanded to rural areas with limited healthcare access. Whilst the model still has limitations such as class imbalances, where only 5% of the dataset experiences stroke, so future work is required to address this oversampling, and the model still misses some key influential lifestyle factors such as diet not present in the dataset that can also indirectly or directly impact stroke risk. Incorporating more diverse populations and patient profiles, the limitation is more of an opportunity. It would be even more impactful in a real-world application if the model were deployed as an interactive, easy-to-use website platform where clinicians can simply input patient data through a user-friendly form. This would help in terms of navigating the complexities of software like Agena, where doctors would not need to necessarily know the technical details of how to go about the software. This would help reduce cognitive load and ensure accessibility of all users, regardless of technical expertise. Thank you.